what we did is we broke this problem up into cases, and we did case 1, and then we took one concentrated load, P1, and we developed a case for it. We developed an individual beam diagram with a cantilever beam with a load, concentrated load at the end. We got VB1, and then we used geometry to figure out VC1 on this side. Remember that the second portion between B and C is linear, and we use that angle here. We multiplied by B to get the extra added displacement at the end of the beam. This time, we're doing a little differently. This is case 2. We have the cantilever beam, but we're just analyzing the 2, and we're removing 1. Then what we're going to do is we're going to aggregate it all after the fact. So what I've done, I think it was William's suggestions, was put this and where I'm getting the table in the back. So if you look on the beam deflection handout and you look at the problem, it's the last problem, you'll see where I've gotten these formulas from. That's coming up. So right now we're just, basically it's almost the same formula, so we can see VC2 right off the bat. So we know that, let's find VC2. And we can do that if we had the general equation for VC2 is, so we have the max, what's called in the back of the book, and it's V max is equal to negative PL cubed EI, and I think there's a 3 under that. So that's where I'm grabbing in the back of the book. We need to actually map this to what we're doing. So we're looking at VC2 is equal to negative, if we draw our coordinate system, the X and the Y. So we're going to have a negative displacement the way we've shown this here. We have VC2 is equal to negative P2. And then what's our length? Anybody know? We have A and B. What would our length be?
Would just be A plus B, correct?
Absolutely, Lee. So we do A plus B, and that gets the quantity cubed. Then we have 3EI. We already know, so the only unknown is on the left side. Therefore, it makes it fairly easy to solve this. So I have a negative 1.788 inches, or 1.79 inches, as our displacement for VC2. So this one is done. Now, since we're done with VC2, we need to find VB2. I'm going to use the deflection, the elastic curve equation. If you look at, again, it's the last column in the image right under the problem. The elastic curve looks like this. We have the displacement, and I'm just right off the book, minus px squared divided by 6EI, multiplied by 3L minus X. So this is the general equation. This doesn't map into what our case is. We have to map it. That's critical for most of these, for students to understand as they begin, because sometimes, if you notice, the L is completely from on in the back of the book. The L starts at 0 and goes to the end. Sometimes you're given the L splits up into thirds or halves or A's and B's, however you want to look at it. So we're going to map this into our problem. How we would do that is we would take VB2. We would use the same force for this case. So we'd say minus P2. And then what X do we use? Here's the question. Or one question. What would our X be in this case?
Wouldn't it just be both of them added together?
No. That's a good thought. What I'm looking at, since this is the curve, my X, I can find any place on the curve. So what place are we looking at on this curve? The blue.
Or X be L?
No, L is the total length. I'm looking for VB, so this is B right here.
X equals L over 2.
Oh, 2.
It's not L over 2, because if we look at A and B, you're Jack. So if we're looking at this point. What's the distance between here and this point here?
Is it just X equals A?
Yeah, it would be X. X equals A at this point. So that's part of mapping. That's the one thing that most students get confused at. So if we're looking right for the deflection at B, in this case, in case 2, looking at the deflection of B, the X goes all the way to where we're looking at. In this case, in case 2, the X is equal to A. So we would say A squared, and then we would say 3, what's our L in this case?
A plus B?
Yeah, A plus B. So we would say 3A plus B minus, here's our X again, which in this case we just did, so it's A. And then we have over 6EI. Does that make sense? Maybe. So we eventually, if we put the numbers in, we would get a negative 0.0374, and that's in inches. So we get about 37 thousandths of an inch deflection at VB with respect to VC. Let me back up with this one. This one is incorrect. That decimal place is over here. It's not 1. It's not 1.78. It's 0.1. So I'm going to write this down. To make sure. That looks high. So if we look at this, we have this curve. It's being deflected only 40 thousandths at this point. And that's undergone by P2. But then all of a sudden, because it's not linear, it's actually a non-linear component, it jumps up to almost 180,000, which is quite a significant jump from 40 to 180. Anybody have any questions? Again, I can do this in the calculus way and figure all of this stuff out, so we don't need the tables. Or I can use the tables for this because they fairly work very easily. So there's multiple ways of doing this.
Maybe it's just me, but it seems like the calculus way is not. I wouldn't describe it as difficult. It's definitely not easy, but it's not. If because we're time things, it's not something we can go over in great detail, especially given the fact that we can look at our answers and see if we did it right.
What were you saying, William?
I'm just saying that the calculus way, because we have the tables and we can see what the answer was that we're supposed to get at the end of it.
Yeah.
It makes it a lot easier to learn or to maybe relearn the calculus part of it. So.
Oh yeah. Sometimes when these cases are known and these you have these tables, that's the way to go. That's why the tables are there. You have to understand the calculus way only because there's sometimes situations you can't do it this way because there is no table for it. For instance, there's no table for like if you want a deflection of suspension bridge or some other different loading, different static loading. So let's move on. We're not done yet. What do we need to do?
Now we need to sum the two deflections together, don't we?
Yep, absolutely, Lee. So I'm going to see how this works. So find VB and VC. VB, we had two cases, and we already found VB1. And then we add VB1 to VB2. That's all we do. Because we looked at it and we can use superposition method. To do this, it fairly makes this fairly easy just to add the two displacements together by the different cases. So in VB, we have a negative 0.056 inches. So both of these cases added together, we get 57 thousandths of an inch by the displacements, approximately. But on the other hand, we have VC gets equal to VC1, which we figured out, and then VC2. We know that VC2 went up a lot due to 2. So that's going to be working out mainly because that's going to be the most deflection at multiple points, and it's non-linear. So we get a high number for this. The number that I got was negative 0.2422 of an inch. If we add the two and we aggregate everything together. And that's how we would find, using the superposition method and these tables in the back of the book. I also want to mention the tables are in your machiner's handbook because everything else is in your machiner's handbook. Any questions?
Are you gonna give us the tables on the test?
Who said that?
Molly.
Possibly, depending on how I want you guys to do it.
Okay.
uh, more than likely, I'm interested in you guys using the tables for right now. The calculus method isn't bad. It's just long. And I'm more interested in using the tables. With that said, there are other things that, when you do a test. First of all, when you do a quiz, I'm not going to put it's going to be something using the tables. It's not, and it's going to be using superposition method if I was to do a quiz. Second, I can't really give you a quiz, but if I was going to give you a quiz, it would just take too long. You don't have that much time to figure out what you want to do, map it out, and then do what you want to do correctly.
Yeah.
So for right now, focus on using these tables, but also be in the back of your mind on the final exam. I could easily put one of these integration ones. Does that make sense, Molly?
Yeah.
Okay. Anybody else have a question? Nope. All right. We don't. Let's move on. And we're going to move on to number 4. So number 4 is a little different. And then we can go on from there. Let me get set up again. Now, number 4 is really easy, but it's not somewhat you'd see and counterintuitive. So let's discuss, and then we can start. So this is number 4. In your book, it's number 37A. Oh, this number 4 came out somewhere. So with that, we have, well, first of all, we have a given, and we have an EI, which is equal to 8 times 10 to the, what is that, 4 kilonewton meters squared. And then we're going to say we have a moment at C, let's call it a moment at C, is equal to 150.
Dr. Fagan.
Yes.
It's kind of off screen for me. Actually, I'm not in full screen. Never mind.
You sure? Maybe I can move it. Is that
Okay, never mind. I got it. I wasn't in full screen.
Oh,
Yeah, it was fine for me.
okay. Thank you. Yeah, don't hesitate to ask any of those questions, even though it might be your doing. Can you read the 150? That's the
Yep.
question. Okay, you can. I still am getting used to how large I can make these. So getting back to, so 150 kilonewton meters. And then we're also going to put in place A is equal to 3 meters. B is equal to 8 meters. C is equal to 2 meters. So I'm trying to find the displacement of 8. So let's look at, and let's draw this out. So I have a beam that's simply supported. So on one end, I have some force of A. I have some force at B. I have a moment at C in here. Now my H is over here. So with that, what's going to happen to this curve? So let's break this up into sections. And I'm going to try this orange. If this orange isn't doing it for you, let me know. So one thing this is going to do is if you think about it this way, if I put a wrench at this point and I force this way, it's going to want to take this beam, this section of the beam, and point it up. All right. So we have this curve here, and this is over exaggerated. It's going to bend, and what's going to happen? It's going to kind of want to go back up. Since there's nothing going on over here, is it going to be, what kind of slope is it going to have? Is it going to have a linear slope or a non-linear slope?
It's going to be linear.
Who said what?
Linear.
Linear. So, and that's kind of common. All right. So it's going to kind of look like this. So there is no table out there that does this. So if we look at this, we have a table that's close to it. And the table that's close to it, you can't really see it in the handout because the thing's small. But let's take a look at what the table looks like. Over here. And I'm just going to draw the table. Just draw the beam here. So we have this beam. We have this force, say 1. We have this force 2. And if I'm not mistaken, we have this moment out here. So this is what the table looks like. This is table, an appendix C. I think that's right. I'm zooming up and seeing. Yeah. So the curve looks like this, where the angle here is theta 1. The angle here is theta 2. Kind of looks like what we're doing, but a little different. One thing to notice is the moment isn't right at this point 1 or this point B. So you have to think about how we're going to do that. Second is it's flipped. And that's it's just a mirror image, so that doesn't become much of a problem. But it is something to think about. So if we didn't know that we can just move this MC to here, we can do what to this? You can look at the sheet, the handout that I gave, the solution. What can we do over here in this section to kind of prove to ourselves that we can just move the MC over to B? Anybody?
It's loading.
I'm sorry?
You can take a cut.
Yeah, we could take a cut. We could take a cut right here. And we can do a free body diagram. So we have MC. We have nothing there. We have no other force there. So we'd have to do an MC here as well. Does that make sense? So this is 0. No other force. That's 0 too. Does that make sense? That means that if we go back to our free body diagram and we take the left side of the cut, I can say that that's MC, and I know that this here is FB. I know that this is FA. That's usually kind of an issue, sticking point with students that does not make this easy to, it's not counterintuitive. So think about that for a little while. But now we moved from MC out here to where B is. It's starting to look more like this, correct? So what we can do is we want to get this angle.
Dr. Fagan,
Yes.
just to be clear, in that last free body diagram you drew,
Yes.
the counter moment for the MC would be the moment caused by FA.
The counter moment along this side of the beam?
Yes.
Yes.
Okay.
Now, we drew this FB wrong, only because the way I drew it is because I'm not looking for it. And I didn't solve for it yet. And we don't need to solve for the forces. It's not a statics problem.
Right.
If you're getting that, Molly?
Yes.
Okay. Yeah, FA is going to go that way. FB is actually going to hold this thing down.
Okay.
But that's a statics problem. If you wanted to solve that, it's not hard. You have the links, and you can do the sum of the moments. You get MC is equal to B times FA, and then you can take whatever that is, find FA, and then take the sum of the forces in the Y direction. We're going to put a coordinate system on here, and notice that B has to be going actually down. So with that may be kind of counterintuitive too. But that would make sense. Say if, like I do apply, and if you were to take this, and I had a wrench, right? I always like to use wrenches because most mechanical engineers have used wrenches. If you haven't, go pick one up and go use it. Something apart. If I hold a wrench here and I push this, if I hold this, what's going to happen, Molly?
If you push it?
Yeah, if I push it, marker is my wrench, and I push this way, it's going to create a moment this way, and it's actually going to, if this is on a pin, that's going to lift that up, right?
Yeah.
So I need something to hold it down.
Right.
That force. Does that make sense?
Yeah, but does that affect the way it's going to bend?
No. That's a good question. So no, it doesn't matter because it's held here and held here. The displacement is what? At A endpoint B, it's 0. Did I lose you, Molly?
Yes and no.
Okay.
But I'll be all right.
That's right. So let me repeat that. At A and B, they're pinned by a pin or a roller.
Right.
All right. That means that there's going to be 0 displacement.
Right.
Overall. Now,
right.
in reality, there is some give, but it's minuscule even to some of this other things. Does that make sense?
That part makes sense.
Okay. So we can assume that it's small relative to everything else. That's a good way to think about it. It's not small, but it's small relative to everything else. You good with that, Molly?
Good with that.
Perfect. So we need to find, going back to this, we have this curve now. If we take this curve and we do this to it, we need to figure out this theta A. All right. If you look in your book, or if you look in the back of your book or on that table, there is, remember it's flipped. This is flipped, so we're actually looking for this theta 2. Here. And we can start to solve this. And we can say that theta 2, you can read from the back of the book, the slope is equal to a moment times an L divided by 6 EI. And I think it's actually negative. Yes. No, it's positive. Sorry. Does that make sense? Or no?
So I got a
Wait,
question.
no, that's wrong. Oh, no, it's positive. What'd you say?
I got a question.
Yeah.
So theta is the angle that the bottom part of that curve makes with the middle of the beam.
Yes.
Because isn't that part not linear? The part that you're making the angle with. I'm just trying to like visualize it. It also looks like you drew it different on this side.
At point A?
Yeah, at point A, or even on the table appendix C part, it looked like you drew the angle in 2 different places. Oh,
Yeah.
never mind. They're
Good point.
opposite, so they'll be
No,
equal.
no. I think I get it. So let's take that. Can you see over here?
Yeah.
Who at Lee? Is that Lee? Is that you or William?
Salo.
Salo, thank you. So I have this. I'm going to draw this line here. I'm going to draw this curve here, right? That slope is a linear slope. I'm taking the tangent of that curve.
Gotcha.
Does that make sense?
That makes sense.
So that means that this angle here, let's call this alpha. That means that is alpha on this side.
Mm-hmm.
Does that make sense?
That makes sense. Yeah, thank you.
So you're right, the curve is nonlinear, but the slope of the tangent of the curve is linear. It's an excellent observation.
Hey, did anybody else just get like the video is like really, really out of focus now? Like I can't see anything. It's all
Yeah, I'm having that same problem.
Are you?
Mine's fine.
There we go. It's better now.
Who's fine?
Mine just says TF.
Is anybody good? I don't know if it's on my end or your end.
it's still really, really blurry.
I don't have any video.
Yeah, I'm not getting any video either.
Yeah, I can't see you, Professor.
Interesting.
I'm getting feed.
Who? Okay.
I don't have a video or anything.
No video. Sailor, are you getting video?
Yeah, I'm getting a video.
Okay. So let's look at it this way. Here's what we can do. If you're not getting any video, look at the solution to this problem. Pull up the solution to this problem. Which we're almost done. Now, everyone have the solution? If not, I can wait.